Or you want to use that one there? Sí.
Sale. Ok. Bueno, muy buenas tardes a todos. El día de hoy tenemos una presentación, un seminario del doctor David Adams y su colega Horvath. Entonces voy a leer la semblanza de David y David va a presentar a su invitado. ¿Ok? Entonces, el doctor David Adams, su investigación se centra en la convección atmosférica, la termodinámica y la comprensión del ciclo hidrológico atmosférico desde una perspectiva teórica de modelación y de observaciones. Después de recibir su doctorado en la Universidad de Arizona, completó una estancia postdoctoral en el Instituto Scripps de Oceanografía y esto fue seguido por una estancia en Brasil de 5 años en el IMPA-UEA y la Universidad Federal de Campiña Grande. Desde el 2012 es investigador titular A del Instituto del entonces Centro y ahora David es investigador titular B del Instituto. Ha formado estudiantes, participa con el nivel PRI de C y es investigador nacional nivel 2, ¿cierto? Ok. Su investigación se ha centrado en la relación entre el vapor de agua y la precipitación convectiva profunda en varias escalas espaciales y temporales, desde condiciones meteorológicas severas hasta el sistema climático global, empleando sensores remotos, satelitales y otras técnicas de observación. Ha dirigido y participado varias campañas experimentales internacionales en la Amazonía central y costera, en la región monzónica de América del Norte, del sureste de Estados Unidos y del noreste de México, y más recientemente en el régimen de los eventos alisios en Costa Rica. También tiene estudios a largo plazo a escala dinámica del vapor de agua atmosférico y ayudó a implementar a desarrollar, la estructura GPS-MET en América Latina, como por ejemplo COCONET y TLALOCNET en el Caribe y México, respectivamente. Bueno, David, adelante. Gracias.
Okay. Gracias, Lisette. Va a ser un poco diferente, digamos, este seminario. Entonces, se basa en un trabajo que Ecos y yo hemos hecho. Voy a dar unos detalles, pero primero pues quiero presentar a Ecos. Si se acuerdan, vino el año pasado en el Panorama. ¿Sí? ¿Se acuerdan? Ok. Y entonces pues hemos seguido en la línea de investigación y tuvimos una nueva idea y pues de hecho se acaba de publicar hace como, bueno, les mandé el artículo, se publicó hace como, no sé, 2 meses, un mes, no me acuerdo bien. Entonces, pero bueno, en fin, ECOS, pues nada más, que tiene muchas cosas, entonces a lo mejor, bueno, voy a tratar de decirlo en español. Ok, es un científico, bueno, investigador del Grupo de Sensoriamiento Remoto, Radiación y Clima en el Instituto de Meteorología en la Universidad de Hamburgo, en Alemania. Su formación de licenciatura en meteorología en el ETHUS.
Yes, ETHUS.
ETHUS. Húngaro. Ok, en Budapest. Sí hizo su maestría y doctorado en ciencias atmosféricas en la Universidad de Arizona, es donde nos conocimos hace muchos siglos. Su área de investigación se enfoca en sensoriamiento remoto, pues usando diferentes sistemas digitales. Ha tenido un puesto de investigador en JPL, en Jet Propulsion Lab, en Caltech, en Pasadena. También en el Instituto de Max Planck, en Hamburg. Y también en el laboratorio Rutherford-Appleton, en el grupo de sensoriamiento en el Reino Unido. Okay. Entonces, bueno, después de su, bueno, no después, pero como resultado también de su panorama, pues desarrollamos un nuevo camino, no una línea, es una misma línea, pero en una cierta, descubrimos que pues en ciertas bandas se puede detectar ¿cómo se dice en español? Brightening. Abrillantamiento y no sé, no apagar, pero ¿cómo se dice? No me acuerdo hablar español. ¿Cómo? Dimming. ¿Cómo se dice en español? Ok. Entonces, y se puede percibir en canales, de hecho, visibles, por ejemplo, de GOES o de los sistemas japoneses coreanos, y también en el infrarrojo, ¿no? Que generalmente suele depender de cantidad, por ejemplo, de vapor de agua. Entonces, y bueno, Ecos obviamente va a dar todos los detalles, pero lo interesante es por la explosión de Hunga Tonga en 2022, esa onda que produjo, que él habló en su charla en Panorama, pues se podía detectar desde de más de 12,000 kilómetros y perturbaciones en el campo de nubes. Y dices, ok. Pero sí, bueno, entonces también eso es interesante de por sí, pero nos da una oportunidad, digamos, para investigar la cuestión de modelación. Piensen en un modelo que, en teoría, pues, ¿cómo se dice? De fina resolución o de micro, de turbulencia, esas cosas, y también tienen sus parametrizaciones microfísicas, etcétera. La idea sería también implementar de lo que verán de la perturbación de presión de la onda y pues para reproducir lo que observamos, que quiere decir que pues el modelo está, ok, está bien. También, no provocamos, no, a lo mejor propusimos una, bueno, en teoría no sería la palabra, pero una explicación un poco, ¿cómo se dice? Um, Especulativa para explicar. Entonces el modelo puede decir, que ustedes no saben de lo que hablan, o, wow, sí es consistente. Okay. Entonces, y el artículo fue publicado y no solamente eso, recibió un reconocimiento, ¿cómo se dice? Un research highlight de la revista Nature. Entonces digo, no, bueno, está bien. Entonces, él va a dar más detalles. La idea es que, pues, pueden, yes. Sí, es cierto, sí. Es que no me gusta, siento como cantante. Okay. Bueno, entonces, si tienen preguntas o dudas así que no se entienden lo que presenta, está bien, pero la idea sería, pues, guardar las preguntas hasta el final, ¿no? Y me pueden preguntar en español si no se sienten cómodos hablando en húngaro. Perdón, inglés. Ok. Entonces, pues creo que podemos arrancar ahora. Ecos, we can get started now. And
Okay.
so, perdón, otra cosa que quería decir, just one second, because I forgot to say something. Que también pues expandimos el grupo de colaboración hasta con alguien de China, del Chengdu, alguien de San Diego State en California, y pues de Múnich y pues en Ecos Institution en Hamburgo. Okay. Entonces expandimos un poco. Okay, bueno, okay, go for it, Ecos.
Okay. So can you hear me all right?
Yes.
Okay. So thanks, Dave, for the introduction. Although I didn't understand most of it, but I hope you only said good things or only bad things. Thank you and also thank you for Unam for this opportunity to present this work at your seminar. I was there last year at the Panorama seminar series, and I had a great time in Mexico City. So I hope to visit again, at least as a tourist. All right. I stopped my video so just to save my bandwidth. Okay, so Dave mentioned that my collaborators. The talk is based on a recent JARA paper that we published. Dave was one of the co-authors, and it's about the effect of the Hunga eruption on meteorological clouds, atmospheric clouds. So not volcanic clouds, but meteorological clouds, which was somewhat unexpected. And oops. So as Dave I understood that much. Dave mentioned that we got a research highlight. This article was mentioned in Nature as a research highlight. We got a write-up on the paper. So I basically stole the title of that research highlight write-up about gave it to me. This is the title of my talk. So the talk will be mostly based on the GRA paper, but I will present some recent results that I have, recent observations that I have analyzed since the publication of the GRA paper. Okay, so most of you, or all of you, probably heard about this gigantic eruption of the Hunga volcano on the 15th of January 2022. Just to set the scene, I'm showing you some satellite images of the eruption. On the left side is the satellite images, an animation from GOES-17 geostationary satellite. Every 10 minutes we get a snapshot, and I'm only showing the first 2 hours of the eruption during daytime. So the eruption started at around 4:15, and as you can see, it produced this gigantic plume, and so these are snapshots every 10 minutes until sunset. So the eruption in the first 10 minutes went up to maybe 20 kilometers, and then 30, and at 4:30, half an hour after the start of the eruption, we got the biggest height of the plume. I show some height retrieval results for this particular image at 4:30. This dome in the middle went up to 57 kilometers. But the eruption was actually going on for like 4 hours. On the right side, I show Himawari images, an animation, also 10 minutes. It basically saw the scene from a little bit different perspective. It's a very similar instrument to GOES-17, and you can see the eruption for between 4 a.m. 4 UTC to 18 UTC, and we got this is the infrared channel. So the left one was the visible channel. This is the infrared channel, so we can see the eruption for nighttime too, and there were eruptions basically going bubbling up to maybe 8 UTC, so 4 hours of eruptions, several plumes, but the largest one was at 4:30. And you see that the eruption generated 2 plumes. The top plume, which is this darker shade of gray, is the stratospheric plume at 30-35 kilometer height altitude, and the white plume is at the tropopause around 17 kilometer. And this is whiter because it's infrared channel. It's actually a colder plume because we hit the stratosphere and hit the temperature inversion. And the stratospheric plume traveled to the west, and the tropospheric plume to the east. Now, we're gonna concentrate on the beginning of the explosion, because this has generated the wave that we are investigating. But this is just a summary slide of the various phenomena that this gigantic eruption generated in the atmosphere and the ocean system. So as I mentioned, the plume went up to a maximum height of 57 kilometers. This is basically in the mesosphere, halfway to space. And in comparison, the Pinatubo eruption went up to 41 kilometers. So this is the largest plume at least in the modern satellite era. And the energy release, the yield of the eruption, was estimated to be between 10 to 60 megatons. The highest and the upper end of the estimate is basically the Tsar Bomba explosions yield. The largest man-made explosion ever produced by the Russians. But even the lower estimate is basically a hydrogen bomb type of energy release. So this eruption generated a bunch of waves. It generated acoustic waves, so normal acoustic waves that travel around 330 meters per second. It generated gravity waves, just the up and down motion generated the traditional gravity waves. And this tropospheric gravity waves then traveled to the stratosphere, and they generated secondary gravity waves, which then introduced these travellic ionospheric disturbances in the higher atmosphere, which perturbed GPS and other GNSS signals. It also produced the largest stratospheric water vapor injection. It increased the stratosphere's water vapor load by something like 10%. And a lot of people are investigating the climate effect of this. In addition to all this, it generated this specific acoustic wave, which is called the LEM wave. So it's an acoustic wave, but its defining characteristic is that it only travels horizontally. So you can imagine it's basically a wall of air, and it just moves horizontally. There's practically no vertical motion in this wave. And this is the wave that we're gonna investigate and its effects on the atmosphere. Now, the oceanographers are interested in this LEM wave because as it traveled across the ocean, it generated these meteo tsunamis. So in addition to the traditional tectonic tsunamis, the Hunga eruption also generated the meteo tsunamis, which traveled much faster at the speed of sound than the traditional tsunamis. Okay, so I mentioned that this was the highest plume that ever measured during the modern satellite era. So in this image, I'm showing you two views of the plume at 4:30 UTC when it reached the highest altitude. On the left side is the GOES 17 image, and on the right is the Himawari 8 image. And you can see that they view the plume from different directions. These are two geostationary satellites, but one of them is located west of the Tonga or Hunga, and the other one east. And from these two separate views, we could use a stereo technique to estimate the height of the plume. So the traditional height retrievals are based on brightness, temperature measurements, but they are very inaccurate in this case, especially because we reached the stratosphere and the stratospheric inversion. But in this case, with the stereo, we could have very accurate height estimates. And we did a manual stereo matching, so identifying features, the same features on these two images, and from that you can calculate for the parallax, you can calculate the height. And you see that the dome in the middle, it went up to something like 57 kilometers. And we had one of the first publications by Carr et al. on this record-setting plume. Okay, but what we're focusing on in this talk is this LEM wave that I mentioned. And you probably, if you look at the Hunga papers, the papers published on Hunga, you will see one of these animations basically in all of the papers. These are the GOES West, the GOES 17, and the Meteosat satellites, two geostationary satellites. And if you look at the full disk images, which are obtained every 10 minutes, people look at the infrared channels, and when you take the derivative of the infrared channels, I'll talk about it a little bit, how we produce these visualizations, then you're going to see this circular pattern expanding. This is the LEM wave, the leading edge of the LEM wave, and this LEM wave traveled across the Pacific and then the US, and then it entered the field of view of the Meteosat satellite. So you can see the wave moving towards or across Africa. these are every 10-minute images. And it converged basically, the antipode of Hunga was somewhere in Algeria. And then reflected and went back, and on the 16th. So you saw one of these animations, or see one of these animations in almost all of the Hunga papers. And these animations are based on infrared images. And the infrared images are preferred for this kind of studies because you can track the wave during daytime and nighttime as well. Now, what I'm gonna focus on is also satellite images and geostationary satellite images, but not just the infrared channel, but also the visible channel. So during daytime propagation. Plus, I'm going to use not the full disk images, but I'm going to use higher time resolution images from these geostationary images. So the three satellites that I'm going to use, the GOES 17, which we just saw, the GOES 16, so the two GOES satellites, and the full disk view are shown on the left side of the panel. But instead of the full disk images that are generated every 10 minutes, I'm focusing on subregions which are imaged at much higher spatial temporal resolution. So GOES 17 had a so-called mesodomain, which is a 1,000 by 1,000 kilometer domain, centered a little bit north of Hunga on the 15th of January, and it produced images every 1 minute. So I'm going to show some results from this. On the GOES 6, as the wave entered the conus area, we could use the GOES 16 conus imagery, which is produced every 5 minutes. So the GRR paper is based on purely on the GOES 16 data. And the GOES West is a new stuff that I did since the publication of the paper. Now, as the wave moved across the conus, it moved out of the conus area eventually, somewhere in the Caribbean, but then it entered the field of view of the Meteosat 9 satellite, which is stationed over the Indian Ocean. And it also has an area which is called the Rapid Scan Service, which images the top third of the Meteosat 9 full disk, which is shown here on the right bottom image. And then the wave basically left the conus, GOES 16 conus area, and then it started to enter the Meteosat 9 rapid scan area. And the interesting part of these two 5-minute areas imaged at 5 minutes, is that they capture the wave traveling during daytime. All right. Now, so just to set the scene, this is the conus area on the 15th of January. And this is the 4 hours during which the wave traveled across the conus area from west to east. This is the visible channel imagery. So just to show you the kind of cloud systems that we have. And as the wave enters the domain on the left side, it's still nighttime. And then as it travels across the scene, the sun rises, and we can track the wave in daytime, during daytime imagery. And I highlighted 4 areas here, which I analyze in more detail. One in the nighttime area, west of Mexico, a clear area marked in white, and the cloud area marked in yellow. And on the west side, during the daytime traverse of the wave, again, a clear area and a cloudy area, or partially a cloudy area. So if you watch carefully, you can actually see the title of the paper. So the title of the paper was actually Transient Darkening of Low-Level Clouds. If you follow, if you have a good eye, you can see a very faint dark wave going through this area. But it will be shown much better in a time derivative imagery. Okay. So the other data that we used are surface pressure records at 1 or 2 minute time resolution. So I'm using 2 pressure records, one from Mexico. This is one of the Tlalocnet stations that Dave is involved with, TNLC, and one during the daytime. The University of Bahamas also has a surface pressure record at 1 minute resolution. So these are very characteristic pressure records of the land wave. So this is the pressure perturbation that the land wave introduced. On the top is the Tlalocnet, and on the bottom is the University of Bahamas. So the Tlalocnet is like 9,000 kilometers from Hunga, and the Bahamas is like 12,000 kilometers. Actually, it's the I think the label is wrong here. This is nighttime, and this is the daytime traverse. But the two records these are the pressure perturbations. The two records are very, very similar and very characteristic of the pressure perturbation in the southern part of the conus domain. So you see there are two smaller peaks before the big peak. This is the big land wave that was generated by the 430 eruption. And the pressure peak here is something like 2 or 3 hectopascal. This is the increase that the leading land wave introduced. And 10-15 minutes later, it quickly drops to a trough, a smaller pressure decrease, which is around -1 hectopascal. And then there's some other waves coming through, they're trailing waves. And we're focusing on this big one. This is the big signal, this big pressure increase. And one thing that you can notice is that there's an asymmetry. The pressure increase is larger than the pressure decrease. So the positive phase of the land wave is stronger than the negative phase. So it dominates basically the signal, the pressure increase. Now, this is actually something that's characteristic of explosive shock waves or big man-made explosions too. On the bottom, I'm showing an image from a man-made explosion, which they exploded like 80 tons of explosives to test actually the global nuclear explosion detection network, which operates pressure sensors and ultrasound sensors. And the top right image is the pressure measurement from an explosion like this. And what you see is the same asymmetry, that the positive pressure signal is usually larger and sharper than the negative phase of the explosion's pressure signature. So it will dominate its effect will dominate. The negative phase also lasts longer, so it's a smaller signal, and it recovers in a longer time period. So the big thing is this big shock, quick positive pressure shock. Now, what we're gonna do when we visualize the signal is we're not gonna actually take this pressure signal or its manifestation in the satellite imagery, but we're going to take the derivative, the second derivative of the signal, because this is what shows up very well in the satellite images. So a positive peak will show up as will be represented by a negative second derivative, and a local minima will be either in pressure or temperature or reflectance, will be characterized by a positive second derivative. So that's what we will visualize in the satellite images. And we can do some back-of-the-envelope calculations. If we assume adiabatic compression, then this positive 2-3 hectopascal increase, pressure increase, will generate a 0.2-0.3 Kelvin temperature increase. The negative phase will, of course, generate a cooling, but it's much smaller, and it's spread over a much longer period than the positive temperature increase. Okay, so I mentioned that we visualize the waves in satellite imagery, but by taking the time derivative of the images, and this is what's shown here. On the top left is a visible image of around close to the Hunga eruption. So it's the GOES 17 mesodomain. The right is the brightest temperature, channel 11 brightest temperature. And if you animate these images, then you're not going to see the waves very well. But if you take the first or the second derivative of the images, so basically you just take the subtract the images from each other, then the waves show up. So if you take just the first derivative, the waves already show up, and the cloudy background kind of diminishes. But the best is the second derivative, where the waves show up the best, and the background, noisy cloudy background, sort of disappears. So we're gonna analyze the waves using the second time derivative of the images, both the brightest temperature and the visible channel imagery. So how does it look over the conus area? So this is the conus area, and this is one of the water vapor channels from the GOES 16 satellite. And this is the LAMP wave as it goes through the domain. This big dark band is the LAMP wave. Now this is an animation showing images every 5 minutes. Between two images, the wave travels around 100 kilometers. Now, in the brightest temperature images, the leading LAMP wave, the speed pressure increase, shows up as a dark band. And dark means, because we are visualizing the second time derivative and using a color scale, where dark means it's a negative second derivative. So it corresponds to a positive increase, local maxima in the temperature. And this is what everybody did. And then we looked at a special channel, channel 7, which is a brightest temperature, an infrared channel, but it's a hybrid channel. It also contains solar reflectance during daytime. So during night, I mentioned that during the passage of the wave across the conus area, the wave hits sunrise somewhere around this area, around Florida. And then we're going to get a solar reflectance contribution in this channel too. So what you will see is that first during nighttime, the LAMP wave is dark, and then in the second derivative image, and then it goes to white, which means that the second derivative flips signs. So in the beginning, when we are during nighttime, in this brightest temperature channel, the band is the signal is dark, so it's a local maxima. It's an increase in the temperature, like in any other brightest temperature channel. But as we hit daytime, the signal turns into white. You can see it's now white, which means that now we have a minima in the brightest temperature. And this basically suggested to us that during daytime, the signal is actually negative, and it overwhelms the positive temperature increase during nighttime. So that prompted me to look into the visible channels as well, which most people, or up to that point, neglected. So now this is the channel 1 blue band visible channel, and I'm showing the second derivative of it. The big white area is during nighttime, so it's just no signal. So then the sun rises. This is the terminator here, and then the wave travels across during daytime. And what you see is now it's a white band, which means it's a negative. It's a negative anomaly. So it's a decrease actually in the brightness signal, the reflectance. It's seen very, very well here. So while in the infrared channels we have a local maxima due to the pressure increase, here we have a local minima in the reflectance channels. And that was kind of unexpected. So what I'm showing here is now all the channels during all the brightest temperature infrared channels for the nighttime passage. So we have 10 brightest temperature channels. This is the nighttime area, so we are west of Mexico, and there's some variation in the signal, but it's always black. So it's always a positive anomaly, a temperature increase in the brightest temperature channels, which we have during nighttime. Now, we're switching to the daytime area, so somewhere in the Caribbean, this is the island of Hispaniola. And what we, now again, just showing the brightest temperature, so the infrared channels. And in all the channels, the signal again, in the second derivative field comes up as a dark band. So it's a increase in the temperature, with the exception of this channel 7, which I showed, which is a hybrid channel, which shows the opposite signal. It's a decrease in the brightest temperature. And this is due to the contribution of the solar reflectance signal. And during daytime, we can now look at the visible channels. We have 6 visible channels, and all of them shows the signal as a negative, as a positive second derivative. So, which is colored as white here. So it's a negative, a local maxima, sorry, a local minima in the reflectance. And what I'm doing next is I will show results for these cloudy and clear areas, show time series of the brightest temperature and reflectance anomalies. Now, the two cloudy areas that I analyzed during daytime and nighttime are shown here. So on the top is the nighttime cloudy area, this yellow areas for which we show in the next slides, the brightest temperature and visible reflectance anomalies. It's a low-level cloud, and the scene is not completely cloudy. There's some clear sky areas and some clouds, and this is a low-level cloud, so around 500-meter cloud of height. And the bottom 2 image show the daytime cloud field, and it's still liquid cloud around 2-kilometer altitude. And I'm going to show the mean brightest temperature and reflectance anomalies for these regions. The previous animations I showed you were downgraded to 2-kilometer resolution, and here I can show you the highest resolution red band, which is a 500-meter pixel size for the daytime area. On the top is going to be just the raw imagery, and the bottom is the second derivative. And what you see is this white band going through the scene. And if you have a good eye, you can see it's a little bit of a dark band traveling through you can see it in the raw imagery too. Now, so taking these, the next 2 slides basically show the brightest temperature and reflectance anomalies, mean anomalies for these regions. So this is the nighttime imagery. On the left side is the night clear area, so there's no clouds in it. The right panel is the night cloudy area, and we have it's a stacked plot. X-axis is time, and we have 10 infrared channels. The time of the lamp peak's arrival is here at 12:01 on this image. And the take-home message here is that you can see a positive anomaly as the pressure peak travels through the scene. It's always positive, so it's an increase, temperature increase. And 10 minutes later, there's a little bit of a smaller temperature decrease. And in the night clear area, the signal is maybe 0.08 Kelvin, positive anomaly. In the cloudy region, you see the same. It's still a positive anomaly, very obvious positive anomaly as the peak travels through, but it's a much larger signal, it can go up to 0.2, 0.3 Kelvin when we take the mean brightest temperature of the sea. So this is all what expected, and that's what gives us this bright, so this dark band when you take the second derivative of the data. Now, this is the same, but for the daytime area in the Caribbean. The land peaks overpass time is around 15 or something like that. And now we have 16 channels. We can add all the 6 solar reflectance channels, which are shown at the bottom. In the clear area where we have no clouds, you see no signal in the reflectance channels. So the surface properties weren't changed by the Lamb wave enough to increase or decrease the reflectance. In the infrared channels, you see the same picture as before, a slight positive temperature increase due to the pressure compression of the air. On the right side now, things become more interesting because the 6 bottom figures or curves show you the solar reflectance anomalies. And as you can see, it's the opposite of the brightest temperature signal. So in the infrared channels, even in the daytime cloudy region, we get the same picture. It's a positive temperature increase. But in the solar channels, plus the channel 7, which is a hybrid channel, you get a negative anomaly. So it means that the reflectance of the cloud, so the cloud is seen decreased. A temperature increase and the decrease in the reflectance. And it's around the 10% decrease in reflectance, which is significant. Okay, I'll basically skip this slide. It's not that important. So in this image, in this slide, I'll now focus on just the time around the passage of the Lamb wave. So it's the same figure as before, but it's only half an hour, 35-minute time span around the passage of the Lamb peak. And you see a bunch of curves. So left panel is the brightest temperature channel, and the right one is the solar reflectance channel. You see a bunch of curves, and the series of curves represent when we restrict the averaging of to thicker and thicker portions of the clouds. So when we average everything, we get this top curve. In this channel, a 1.3 Kelvin temperature increase, brightest temperature increase. And then as we only average thicker and thicker portions of the clouds, so we're moving into the center of the cloud, the signal, the brightest temperature increase becomes smaller, and the opposite happens, or the same happens, but in the visible channel, the darkening or the reflectance decrease becomes less and less as we move into the center of the cloud. So what it suggests is that the signal that we see is mostly due to the thinnest portions of the cloud, so the cloud edges and the surrounding areas. And this is our speculative explanation, what we came up with, how to explain this opposing signals in the brightest temperature and the visible infrared and visible channels. So what we have is we have the oceanic environment, and you have the ocean surface, we have some aerosols, and in cloudy regions, around the clouds, there's this so-called transition zone, and there are lots of papers. It's a hot topic, this transition zone around the clouds. The cloudy environment smoothly eases into a clear sky environment. So around the clouds, within a certain region, we have also these humidified aerosols. The relative humidity is relatively large around the cloud edges, and if you have certain type of aerosols, they can grow in this humid environment. And of course, this humid environment controls how the relative humidity will control the size of these humidified aerosols and also the cloud droplets. So this is this transition zone or humidity halo. And because of these humidified aerosols, the reflectance around clouds, even though it's so-called clear air, so there are no cloud drop particles, the reflectance is larger than in the far field where we only have dry aerosols. And this is a measurement from an aircraft campaign where the people measured the relative humidity and also the reflectance properties as a function of distance from the cloud. This is the cloud edge at 0, and 4 kilometers is the far field. So as we going closer to the clouds, the relative humidity increases, and within a kilometer of the cloud, the relative humidity is 90% and goes to 100%. So it's a sharp increase in the relative humidity, and in this narrow area around clouds where you have a very sharp increase in relative humidity, the scattering properties, the scattering factor of aerosols also is very sensitive to the humidity and increases very sharply, especially for marine aerosols, which are very hygroscopic due to salt. You see a very sharp increase in the reflectance of these particles. And because of this, this image showed the ME calculations, and the right bottom image now shows actual reflectance measurements from aircraft. And you see that the reflectance quickly increases in this clear air, but around the cloud, relative humidity, large relative humidity, clear air around the cloud. Now, the point here is that relative humidity, a small change in relative humidity can basically increase or decrease the reflectance very sharply. So what happens is that as we have this environment, and don't forget that we plotted the mean over this domain, the mean brightest temperature and mean reflectance. So it's a combination of clear air and cloudy air. So as the lambda wave goes through, the pressure increases. It increases the temperature, the air temperature, by 0.2 to 0.3 Kelvin, and it will lead to a reduction of maybe 1-2% reduction in relative humidity. And because these aerosols and the reduction in relative humidity will have an effect that it will evaporate the smallest cloud droplets and also reduce the size of these humidified aerosols. And this is what I try to basically visualize here with this little schematic, that as the lambda wave goes through, the cloud drops and the humidified aerosols shrink, which means that from space we see more of the surface. And the surface is dark and warm, while the clouds and these humidified aerosols are bright and cold because they are strongly reflecting, plus they are at higher altitude. So as the lambda wave goes through, the satellite will see more of the surface, which means that in the brightest temperature infrared channels, we're going to have an increase in the temperature, and in the solar channels, we're going to see a decrease in the reflectance. So this is our explanation, or a speculative explanation for this phenomenon that we see. Now, the next slide is sort of a summary of what I've shown so far. It's an animation of the lambda wave's passage back and forth over the Caribbean, and on the right side you see the second derivative of the visible channel. And the lambda wave is very obvious. This white band moves back and forth. So I'm eliminating forward and backward in time, so just to make it more clear, the passage of the wave. So in the second derivative image, it's very obvious that the lambda wave, and it's a negative, it's a positive second derivative. So it's a minimum in brightness in the reflectance. Now, on the right side, I show the raw imagery. And if you have a good eye, and if you watch carefully, where you see this white wave moving, you should see a black wave also moving. So the decrease in the reflectance can be seen even with the naked eye, because it's a 10% kind of decrease in the reflectance. So this is what I've done for the paper. And how much time do I have left? Maybe 5 minutes, 10 minutes? I could.
Let's try to do 5 echoes if you can.
Okay. So basically the point is that we could track this signal, the effect of the lamp wave, somewhere up to like 12,000 kilometers from Hunga. You can still see this decrease in the reflectance. And with the Meteosat 9, we could even track further. The wave travels across the rest of the Atlantic during daytime. And okay, I'll leave this out. So this is a slide from now even further east than the Conus area. The Conus area covered distances up to maybe 12,000 kilometers from the source. And the point is that we see the same thing even further east. In the Meteosat domain, it's just one snapshot. In the brightest temperature, you see this increase, so positive warming signal. And where it's a dark band in the brightest temperature infrared channels, you see a wide band, so a reflectance decrease actually in the reflectance, solar reflectance channels. So it's up to maybe 16,000 kilometers. So we can see from the Meteosat data that even further, the effect of the Hunga goes even further, up to maybe 16,000 kilometers. And this is my final slide then, or final images that I show. And I also found some ground-based footage from very close to 70 kilometers from Hunga. There was a guy who posted a YouTube video that he took from Nuku Alofa, I think, where he videotaped the traveling of the wave, or the effect of the wave from his GoPro camera. So this is the location where he was at the end of the arrow. And then as the plume expanded, then he was actually underneath the big umbrella. And the next animation is a 20-second footage from the ground, which basically confirms our explanation that as the pressure wave goes through, the air heats up, and then because the decrease of the relative humidity, the clouds drops evaporate. I sped it up by a factor of 2, and what you see, hopefully, is that the clouds basically disappear. Again, this is 20 seconds. So the wave went through over his house in 20 seconds, and at the beginning of the animation, it's cloudy, and then basically as the air warms up, it becomes clear. I hope you can see. It's not the best footage, but this is the best we have, and you can now see the blue skies. And of course, as the negative phase of the wave came through, then the clouds recovered. So basically, this is what we see, but not from the ground, but from space. As the clouds clear up, you see more of the surface, which is usually darker and warmer than the clouds. So to me, this is a very strong suggestion that what we proposed actually is the right explanation. And these things happen very quickly, in a second or 5 minutes, 10 seconds to 5 minute time scales, which also suggests that this is a thermodynamic adjustment, cloud adjustment to these perturbations. Okay, so let me just summarize them for the sake of time. So the Hunga eruption generated globally propagating atmospheric pressure, temperature, and relative humidity perturbations. This is what we call a LAMP wave. These temperature and relative humidity variations then resulted in the periodic condensation and evaporation of the smallest cloud droplets and these hygroscopic aerosols in the so-called transition zone of the clouds. This is what we proposed as an explanation for what we see. And due to these evaporation and condensation cycles, the cloud optical properties also varied. And they varied as the satellite imagery and the ground-based imagery confirms on very short time scales, 10 seconds to 1 minute or 5 minutes. We also have 1 minute imagery, which I didn't show. I ran out of time. And this very short, very fast variation of these cloud optical properties suggests that these clouds adjust to the LAMP perturbation. It's a thermodynamic adjustment, not dynamic adjustment, turbulence or other schemes or processes which operate on a longer time scale. Now, the interesting thing is that the periodic growth and shrinkage of clouds then resulted in brightness variation, which we could detect from satellites. From the surface, we have imagery from 73 kilometers, which confirm that this is what's happening. The clouds expand and shrink. But the novel thing or the cool thing is that we see this effect from satellites as far as 20,000 kilometers. I showed you the meteosat imagery, and I could even track further. So my current estimate is that we can see this effect 25,000 kilometers from Hunga. So for the future, what I plan to do is we can use Himawari 8 and the Korean geostationary satellite, which are even further east than the meteosat, and also cover the wave passage during daytime. And we can basically put an estimate on how far away we can see this effect from Hunga. The current distance is 25,000 kilometers, and when we look at this other satellite data, we can maybe see it even further, effect even further. And the other important thing is that this is the Hunga wave is a natural produced. It's a natural laboratory. We can use this phenomena to basically test and validate cloud models. If the parametrizations and the microphysics schemes in the LES and other cloud models are correct and accurate, then these models should be able to reproduce this fast 10-second minute scale brightness variations in the clouds if one imposes one of these, the LAMP wave with perturbation. So we throw it out in the paper as a challenge to the modeling community that can the models reproduce a 10% decrease in reflectance if they impose a 2-3 hectopascal increasing pressure on their clouds, on the cloud fields. So this is what I have, and I stop here.
Because what was the slide that you have with the airplane and the bomb and all that kind of stuff?
Well, I skipped it through due to time.
Oh, okay. Yeah. Okay. Just
So,
basically giving an explanation of why you have this kind of condensation behavior with waves.
So basically, I said that the explanation is in this generic, in the broad group of condensation phenomena. Whenever you have any kind of perturbation in the temperature or pressure, you will get temperature increase or decrease. And when the temperature increases, then things will evaporate. And during the temperature decrease, things can condensate. And in our case, the temperature increase is the dominant signal. But in many other cases, it's actually the temperature decrease is the dominant signal. And this is what we see, for instance, the nuclear explosion. So on the right side, we see a nuclear explosion, which is a very good, relatively good analogy in terms of energy release of the Hunga. And what you see is these expanding condensation rings. As the pressure perturbation travels and expands, the air cools. So it's the same thing what we see from the land wave, but here the negative anomaly is the one that dominates. So we see the expanding condensation ring. And on the right side, top right, you see that nuclear explosions can produce a lot of these condensation rings. So this is what we see, but we see its counterpart, the positive temperature increase. So the evaporation, that's what is dominant in the satellite signal. And it happens basically anywhere, anytime you have any kind of temperature decrease due to, for instance, turbulence, when you have aircraft wake and tip vortices, and the pressure decreases, and then things cool down, or in the vapor cone, or in the Beirut explosion, similar to the nuclear explosion. Again, you see these condensation rings, the negative phase of the pressure perturbation. So these are the same group of phenomena, but here the negative phase, while in the satellite images, the land wave, it's the positive phase that dominates the imagery. Yeah.
Okay. All right. Thanks. Okay. Well, I guess,
I'm open to any questions.
Así como de preguntas. Okay. Son muchos. Okay. Bueno, en húngaro.
Te puedo preguntar en inglés, pero quieres le traduces tú si quieres.
Bueno, actually English is fine.
¿Sí? Yo te lo digo a ti, tú le traduces. O se lo digo directo.
Si prefieres. A ver si.
Entonces, hagámoslo. Tengo dos preguntas y 0 teléfono. Ok, mi primera tengo una pregunta que no me quedó muy clara. Estas land waves se propagan a 340 y tantos metros por segundo. ¿No?
I did 310, no? Because what's the propagation speed of the land waves?
So the land wave is an acoustic wave. It's the speed of sound, 330.
So it is the speed of sound.
Meters per second.
O sea, desde Hunga hasta el océano más lejano transcurrieron un montón de horas. ¿No?
So what was the total time that it takes to, like, let's say, reach its point of explosion? How long does it take to propagate across the world?
It travels at the speed of sound, so like a jet line or a little faster. It started at around 4:30 UTC on the 15th, and it reached the US, I don't know, 8, 9, 10 hours later. And so it's 1,200 kilometers per hour. So
Okay.
Mi segunda pregunta es, esta erupción del volcán puso material a 50 kilómetros de altura. Ese material, entre otras cosas, también se menciona una inyección importante de agua, ¿no? De H2O, pero también introduce mucho material de otro tipo, partículas. Eso también contribuye al dimming de la radiación en términos generales.
Oh, okay. So like in terms of the other groups that are investigating the injection of Hunga into the stratosphere. So there was, like you mentioned, there was the biggest shot up of water vapor, but there's also a lot of aerosols, particulate matter that actually also goes up, and I would assume stays there. Are other people doing research on that one?
Yes, so there will be a report actually coming out at this year's AGU on the upper atmospheric effects. So there's a French group which used balloon measurements from Reunion Island, and there were other measurements. I think even from Brazil, some high altitude balloons. So the water vapor spread all over the planet in 2 years, and it can still be, the signal is still there from satellite imagery, and the aerosol plume is also still measurable from space and also from these balloons. So there's long-term balloon measurements looking at how the plume spread. It eventually or initially it spread longitudinally, and it took like I think 2 years or a year or something like that to spread over the entire globe. But its effects, its surface temperature effects are much smaller than, for instance, Pinatubo, because it was a very water-rich eruption. So the properties of the clouds, the ash and other particles that it generated, sulfate, whatnot, are different because of the water vapor injection.
Okay. Way in the back there.
Hola,
Es que no veo bien.
soy yo, Jimena.
No, Jimena, no puedes preguntar en húngaro. Okay, go ahead. Sí, adelante.
Igual en español y usted se las traduce, por favor. Pues primero que nada, muchas felicidades. Está padrísimo su trabajo. Para alguien que trabaja con imágenes satelitales, me emociona muchísimo toda la metodología que desarrollaron. Y justo quería ver como a qué otros tipos de fenómenos se podría aplicar esta metodología o partes de esta metodología. Por ejemplo, no sé, de los que mencionaban, o como ondas de montaña o algún otro, o sea.
Okay. So basically, I know you've applied this technique to a lot of other things. What are some of the other, independent of the volcanic eruption, like mountain waves, different types of gravity waves? What other types of phenomena have you done this, like second derivative, first derivative?
So you can apply this to gravity waves, and we did that. So this kind of second time derivative imagery can be applied to gravity waves generated by deep convection. So when you look at the CONUS area or this high time resolution GOES meso domains, you can see gravity waves propagating from deep convection, and also other volcanic eruptions, La Soufriere and other tropospheric volcanic eruptions generated gravity waves, not land waves. So, but gravity waves which can be tracked from this kind of satellite imagery. La Soufriere, we looked at, and you can see gravity waves from La Soufriere traveling at much smaller
I
scale.
remember your study where you were looking at like the islands off the coast of Mexico and the coast of California, and you have was that just visible where you're looking?
Well, that's the vortex stream, but that's
is that just visible or?
Yeah, it was just cloud tracking, tracking the clouds and the wind measurements. But this time derivative imagery is good for waves. And gravity waves, when from deep convection and volcanic eruptions, can be also tracked. But those can be tracked for a shorter period of time. So the Hunga generated not just gravity waves, which travel 10, 30, 50 meters per second at most, but this big land wave. But smaller eruptions, La Soufriere, Icoca, others, did generate gravity waves, and you can also see them in this kind of geostationary imagery with this time derivative technique.
Okay.
So you can estimate the properties, frequency, wavelengths, that kind of stuff.
Muchas gracias.
Oh, okay. I'm sorry. Okay. One more. I don't know, how are we doing on time? ¿Cómo vamos de tiempo? ¿Ya nos pasamos?
Bueno, es muy interesante esta explosión del volcán que genera estas ondas de LAM, que por lo que observé tienen una longitud de onda como del ancho de la República Mexicana. Quería preguntar sobre la relación termodinámica durante el desarrollo de esta onda de LAM, en donde se dan incrementos como de 2 milibar en la presión asociados a incrementos de temperatura como de 0.3 grados, algo así, según recuerdo. Si estos incrementos en la presión y la temperatura, esta relación termodinámica está asociada a una tendencia a mantenerse la densidad constante durante el paso de la onda de LAM.
Okay. So basically, he wants to know if we were just assuming constant density as the Lamb wave passes through, just thinking of like the ideal gas law. So just what you got is a pressure perturbation, and the density stays constant, and then you get a temperature perturbation.
Yes, so I mean, these are low-level clouds, up to 2 kilometers, and we just did the typical ideal gas law and adiabatic compression. And of course, if you go up to higher altitudes, then you have to also the perturbation, the pressure perturbation also decreases exponentially with height, so that would also have to be taken into account if one goes to higher altitudes. But in the imagery, we don't see, for instance, effects in ice clouds. So it's basically liquid clouds that we see some visible changes. And in the bottom of the atmosphere, I guess these were reasonable assumptions. And there were actually measurements. So people try to measure or analyze, see the temperature increase even from surface measurements. So meteorological sites, some of the sites also have, you measure the temperature, and it's difficult, but there was a Japanese group which looked at a bunch of surface stations in Japan, and they could sort of see a 0.1, 0.2 Kelvin temperature increase in their temperature data when they combined lots of sensors. So in individual temperature data, the temperature change doesn't really come out, or very difficult to pull out, unlike the pressure. The pressure, basically, you look at any pressure data on the 15th and the 16th of January, you see the pressure signal, but the temperature signal is much smaller. But they pulled out a temperature signal which is kind of comparable with our calculations. So I think it's a reasonable estimate that 1 hectopascal increase pressure would give you a 0.1 Kelvin increase in temperature in the lower atmosphere.
Oh, okay. Thank you very much. Sí, una segunda pregunta.
Nada más 15 más.
Porque había otro incremento o decremento asociado con estos incrementos en presión y temperatura. El otro es un decremento, al parecer masivo, en la humedad relativa. Este decremento en la humedad relativa se debe a la gran cantidad de agua que se genera durante la explosión, porque vimos otros ejemplos de explosiones. O también hay una relación termodinámica entre cambios de presión y cambios de temperatura. Okay.
Bueno, creo que puedo rápidamente. Yo diría que, por ejemplo, como está muy lejos del sitio de la explosión, es nada más la compresión, expansión, y ya estamos asumiendo adiabático, y ya con eso. Entonces, como él trae en su figura, hay este gradiente de casi 99% de humedad y luego 90, algo así.
Sí.
Entonces, con la compresión, expansión muy rápido, pues se puede evaporar y condensar.
Okay.
Aunque sea muy, como se dice, débil, esas perturbaciones. 3% de humedad relativa en esa zona es suficiente para impedir o producir condensación. Bueno, eso es nuestro argumento. obviamente hay que confirmar, ¿no?
O sea, esencialmente es un proceso adiabático que se da.
Sí, sí.
Ok, ok. Gracias.
Okay. Benjamin, ¿tiene pregunta? One more, well, another question. Sorry.
No acabo de entender un poquito esto. Esas ondas son de presión, ¿no? O sea, sonido.
Yeah.
Se comprime y se expande. En el ejemplo que puso de Beirut se veía ahí a un cierto nivel, el anillo ese y más alto otro, etcétera, ¿no? Entonces yo supongo que en ese volcán se provocaron ondas en toda la vertical. Y esas ondas son de sonido, dependen del medio en que se van a propagar. Entonces, si tú tienes variaciones en la densidad, vas a tener distintas velocidades de propagación. Entonces vas a tener distintas zonas de compresión y descompresión en la vertical. Por ejemplo, en el Pacífico, en las costas de California, un fenómeno que no sé si ya lo entienden bien es que puede cambiar de estar oscuro, que es mar, digamos, a brillante, que es nube, y son unos patrones muy bien, digamos, bien definidos, que en cuestión de minutos pasan de negro a blanco, y no entienden bien qué ocurre ahí, ¿no? Entonces, en este caso, no pudiera ser que en la vertical tienes cambios diferenciales y eso te lleva a eso, porque lo estás detectando desde satélite, ¿no? No es que estés midiendo ahí con un perfilador exactamente qué está pasando, ¿no? O sea,
Sí.
tú lo ves de arriba y estás viendo algo integrado.
Una superficie, una altura, vamos a decir.
Por eso, y tú ves lo integrado desde lo que puedes ver, ¿no? Entonces, si tú en la altura tienes esas diferencias asociadas a esas ondas, ¿no podría ser también una explicación?
Basically what he's asking, Ecos, is if the vertical, because the propagation is in the horizontal, but there can be vertical variations, for example, maybe in the intensity of the perturbation, and then also considering the density as you get higher. And so what if I'm understanding correctly, what he's asking is that can that also have an impact on what we observed, for example, in your second derivatives, in your first derivatives, or in the visible? Or is that just because it's not cloudy air per se that it's out of the realm? It's not important.
So, I mean, as I said, the pressure perturbation decreases exponentially with height. So most of the energy of the land wave is in the lower atmosphere, and these different satellite channels have different vertical weighting functions. So some of them are more sensitive to lower altitudes and some of the higher altitudes, and you see the same signal in all of them. The magnitude, of course, is different. I didn't go into detail on that, but so yeah, there are some vertical variations, but it's always a positive signal. So, and I also looked at the curves that I showed you were not second derivatives. Those were these curves here. These are the raw temperature data. So we use the second derivative to identify where the wave is, and then we look at, we select an area where the signal is strong in the second derivative, but then I'm only analyzing the actual brightness temperature reflectance anomalies. So there's no derivative here. It's just the raw temperatures, but removed like a 35-minute running mean. So I don't know if it answers the question, but these results here have nothing to do with the second derivative. The second derivative is used for visualization. But technically, from the second derivative, you can actually also pull out the temperature and reflectance.
Mira, quizás si le preguntas, ¿no? O sea, un Gedanken experimenten, como le dicen los alemanes, ¿no? Tú estás parado y pudieras tener un perfil que tú lo estás muestreando siempre. Entonces la pregunta es, las ondas que van arriba y hacia abajo, porque es sonido, ¿no? ¿Siempre van a estar en fase?
As the wave propagates in the vertical, I mean, as it propagates horizontally, is it exactly in phase through the whole vertical column?
So these are good question, but it's not very well known. So all the theoretical studies on land waves were from the 60s and 70s by Bredetton and others, and they assumed an isothermal atmosphere, no wind. So both winds and the temperature variations vertically and topography, all these things affect the land wave propagation. The classic studies say that it travels, there's no phase difference. But there are some new papers came out this summer or earlier this year, I think by some Chinese groups, where they used actually GNSS, GPS signals, and they claim that there's actually a tilt in the wave. So depending on the 50s, it's sort of tilted eastward. On the 16th and 19th, when they came back, it tilted the other way. So there's some new results which append or basically show that what you get from the isothermal atmospheric ideal models is the real life is more complicated. So there's some tilt to it, but a very small tilt. There are 2 papers in GRL by Chinese authors which deal with this. So the good thing about this land wave is that it gives an opportunity to validate all these wave propagation models, and most of them are based on linear theory. So there's lots of new details which came out from the analyzing the land wave propagation. Wind, for instance, including winds, was a very important effect, which one of our co-authors, so Ignacio is a co-author on our paper, and he showed that you have to include winds, global winds, to describe or model the observed land wave signal that you observed in the satellite data. So these are all good questions, and this is the first time since the banning of atmospheric nuclear explosions that you have this land wave. So in the 60s and 70s, the nuclear explosions did generate land waves, but that time the global measurements network was much worse than what we have today. So it's ripe for improving models that were developed in the 60s and 70s.
Okay, because I think we'll call it to a close here. Do you want to bring your boys in and to say hello to everybody here in the audience?
No, they are not here.
Oh, okay. They're sleeping?
No, they are still, I think, ice skating training or something like that.
Ecos is in Oberstdorf, in the southern part of Germany, on the border with Austria. Okay, so all right, bueno. Thank you very much, Ecos, for the talk. If anybody wants to have contact, send me an email and I can put you in contact with him for papers or questions or whatever. Okay. So, all right. Thanks, Ecos.
Okay. Thank you for your attention.